welcome to the talk, Disambiguation, the black technology. Um, many people, some people told me that the title is not terribly meaningful. Um, I'm sure that's it because they don't watch enough Japanese animations. So they don't know what black technology means. If you go Google, it will tell you it's a kind of technology too higher than the current society. But okay, the talk is not about technologies. The talk is about controlling overloading set. When, how, and why. So why I give this talk? When the C++ now 14 is asking for submissions, I saw a suggestion to talk about some spinning magic. My first reaction is that that's not magic. If you watch some something like Harry Potter, you'll find what magic is, right? You use some spells. Sometimes it works, sometimes it does not. Different people use the same spells have different effects. But technology is not. We know how it works, and this is why the talk is here. But for some reason, some people are scared about controlling overloading sets. I copy-paste this from the meeting notes, so don't come to me for disclosure. And someone said, I rarely have needs for anything but a normal function binding. Translation, controlling overset is abnormal. But sometimes the abnormal thing is not your code, it's the language. For example, this is I titled this as a real-world example, but that's not quite true. I just want to scare people who only look at the slides. This is a problem we found in our unit test code. So the question is, what happens if I write this? Mm-hmm. Uh-huh. Oh, excuse me. I'm sorry. It's a question I'm asking. So I want to. Oh, okay. He says. Oh, okay. He says it's a problem because you are going to reach the first overload. Yes. And I think everyone agree with that the second should be reached. And here's why. So I give the call a string literal. The type of string literal is a character array. Then the language look at the variable function set, and it says, let's first do argument adjustments, which includes array to pointer conversion. I believe this step is already wrong. Why? Because look at this type. What is the possible value range of this type? 0 to some number, right? It's a pointer. This is an array. And with a length. The possible value range of this type is 255 or 254, order 33. It has nothing to do with this type. And I don't know why there's an implicit conversion to convert an array to a pointer.
Because C.
Yes, because C. All crap comes from C. And it's not the worst thing. The worst thing is that this conversion is considered as an exact match in the standard. So, okay, we don't talk about the conversion stuff that much. Let's move on. Next step, we find out that it's a pointer, and there's another standard conversion. Says the pointer is implicitly convertible to bool. It's called Boolean conversion. I claim that that conversion is also wrong. Why? The possible value range of this type is 0 to some pretty big number, and the possible value range of bool has only 2 values. How can you just shrink a large range of values into 2? That can't be right, right? This one is possible to match this one, the first overload. But here we have a second choice. What do we do with that? So the standard finds that this is a class, which is a user-defined type. So you look at all the implicit conversion constructor of this type and says, yeah, there is a user-defined conversion which converts the character pointer to string. But it's a user-defined conversion. All others are in the standard conversion sequence. All user-defined conversion comes after the standard sequence, conversion sequence. I already said.
So just a question. I'm wondering if standard string had a constructor which took char const.
It has.
Then what? Did that change what happened?
Wait, excuse me. If standard string has a constructor which took.
Reference to char const n.
Oh, you mean, okay. If the question is what if standard string has a implicit conversion constructor which takes a reference to array type instead of this.
Still think that defined conversion has more priority.
Yes.
It wouldn't, the decay wouldn't occur.
No,
It would still prefer to decay before applying the bool. Okay.
so because of this rule, we lost the only chance we fix the problem in the class type itself. So here, three conversions we do. All of them are wrong. The last one is wrong not because of itself, just because of ordering. Okay, so this is the first step we do when I do when seeing an ambiguation problem. And by the way, just keep this in mind. We already know that when we compile that, there's no warning and the code just runs, and there's no ambiguation, language-defined ambiguation problem. When I say the ambiguous, I mean there's a gap between our understanding and what the language understands. Okay, this is the first step. Analyze. Why? Next step I'm going to do is I found a quick fix. It's not a disambiguation, but it quick fixes the problem by changing your input. It does not solve the problem because if someone else write new code, they don't have the fix. They may not have the fix, right? The problem is not solved. But by looking for a quick fix, we know what we want to do, what is right. Right? We want the second overloader to be called. After we know what is right, let's go back to judge whether the old one is right. There are a couple of answers to these questions because this has something to do with the meaning you want to express by invoking the original code. So it might be a case as you can see, this is string literal, right? How you call some function with a string literal and don't expect it to be passed into some string like toString, right? It looks like this call is valid. If we answer this yes, then we have a couple of options to solve it. Maybe we can just add one overload which takes a character pointed to a character string. Why that work? Let's go back to this. We know the user-defined conversion is what we want, right? Only the ordering is wrong. So by adding a overload to here, we functionally change the ordering. So that fix will solve it by fixing this conversion. And we might have other option. We can say the Boolean conversion doesn't make sense. So we kill the second Boolean conversion by yield the first, so that we yield the first to the second, because we are going to talk about the technology used behind to achieve this. And we might answer this question to no. Why? Because, as I said, it has something to do with semantics. You see the thing I passed in is the MD5 string. You can't just type a MD5 string on your keyboard and input it, right? You are predict in the future. So it might be a case we just don't want this old code to compile. And we also have a couple of options. We can create the overload and delete it. And we can say, all those conversions doesn't make any sense. I'll just disable all kinds of conversions on this overloaded set. So there are many choices. Choices about bad. But so now you have the choices, and it might be a case you just choose one. But wait, before you choose the choices, let's ask this question. Why those functions are overloaded? Why they are not named differently? So that you don't have this issue, right? This question is much harder to answer to the technology questions, because, as I said, technology is not magic. You learn it and use it, and it works. But this one is strongly related to the design of your function. So here's the plan of the talk. We try to answer this question, this very hard question, first. And the rest of the talk is going to focus on the technologies. And about the technologies we have, we can help you find patterns of the problems we've seen so far. And I can tell you how to solve those problems patterns by patterns. Okay, so let's try answer the technology. When to overload? So overload, when we are saying that, we mean, in this talk, we mean function overload, right? If you don't understand what is the function, you obviously don't understand what's the overload. So let's look at what is a function. There are five syntax in C++ can invoke a function. But if you search for C++ standard for invoke, there is a conceptual unified form. So if, in my understanding, function type depends on the parameter type and return type, and it has a function body. When you run this body, because it's an execution of the function, and the function call is basically passing arguments to fill in those parameter types in an environment, and the function runs. It has a return value which matches the return type, and we got the environment after execution. And we might also get side effects. Any questions so far? Okay, no. So we all know what overload function is, right? They have the same name and might go in the same context, but that's a standard detail. So what is overload resolution? Overload resolution selects execution based on the argument types. The standard, the return type, the type itself, does not contribute to the overload resolution, but the procedure to calculate the return type might. We are going to see examples here later. So this is.
Sorry.
Mhm.
What you just said?
Oh, overload resolution only depends on the parameter type. The return type, the type itself, does not contribute to the overload resolution. But we might have techniques that can calculate this return type. And that process might change the decision of overload resolution.
Process of computing the return type?
Yes, exactly. Okay. So that's how a overload resolution looks like, right? We have multiple argument types, and we select execution, and we like what we have seen. Sometimes language get it wrong, not because the language is wrong. It might be because they have a different thought from what we understand. So, what is disambiguation? And disambiguation? Very simple. You avoid unintended executions without changing the argument types. If you change the input types, I don't consider it a disambiguation. It does not essentially solve the problem. But it might be a case that your code just don't compile. That's fine. Like the word I choose here, it avoids unintended execution. If the program just don't compile, obviously you don't run, so it's avoided. And we can also change it to some your intended overload. That's also disambiguation. Okay, enough about function and functional overload and disambiguation. Let's try to answer that important question: why overload? So, this is how I see a function in C++. When we first learn function in programming, we all know function is like a black box, right? You don't know what it does, you don't know what it executes, and this is exceptionally true for overloading resolution. You really don't know what it executes. But here's what we have for a function. We have input, which is the gray part. We have output, which is the dark blue part. And the execution just takes the input and gives you an output. Okay, here is my thoughts on overloading. Function in the same overload set should give symmetrically the same output. What does it mean? I mean, if two functions are overloaded, it should provide the same functionality. Why? Let's look at this. Look at this picture, right? The execution is a box. You can implement a function in many different ways and takes same input, gives same output. It's just the way how you write code. That's how black box is defined. That's not the purposely create overloaded functions. And overloaded functions takes different argument types, right? These parts still cannot be the same. Only the output we expect them to be the same. Why? Because they are named the same. Well, if they have, if you can only understand two functions' outputs in a different way, why you name them should be the same? Hmm?
No problem.
Uh-huh.
You can't have different names for constructors.
Exactly. I'm going to talk about that. The question is, we don't have different name for constructor. Okay. So, as we said, this is my thoughts. In the same overloading set, function should give the same output. But that does not work very well. As Nico said, we have constructors. They have the same name. And they have to be overloaded. And not all constructors doing the same thing. Although in the standard, most of the constructors doing the same thing. If you find the effects part of the standard, you are going to find effects. A new object after is constructed. But sometimes it's not the case. And sometimes we have other things that not match my hope. Let me raise an question. A question. What still moved us? As did it move? Look at this. CPP reference. Move. Still move. It's an algorithm. Right? We have two overloaded functions. One calls still move, another one calls still move. One is a case, another one is an algorithm. It seems that the standard just don't like my principle. Okay, so since the language, forget about the move part, right? Since the language only has one name for constructors, it turns out to be there must be a strong reason to require people to overload that. But if we have to overload that for doing different things, we have workarounds to solve it. But before showing the workaround, let me show you my fixed principle. Functions that may exist in the same variable function set should give semantically the same output. But you don't know what variable function set means. I think I should explain it anyway. So the overloaded resolution. I think I should just open this. Why? don't know how to close this. Variable function. I guess you just can't see this step. I should prepare this more. Okay, I'll just say. Variable functions means, okay, that starts from overloading resolution. Overloading resolution has two steps. First, it finds the variable functions. You can say they are candidates that might be ambiguous for a function call. And the criteria here is the call and the function may accept the same number of arguments. And there is a implicit conversion sequence to each of the arguments from the call to the function signature. So,
sorry, I'm not following.
When overloading resolution set, it has two steps. First, it finds functions that might accept that call. And the criteria is, first, your call, like FAB, has two arguments. And your function also needs, you also be able to accept two arguments. And the next thing is, your function parameter needs to have an implicit conversion sequence from your arguments. Like your call is FAB, and your function type is char int AB, needs to be implicitly convertible to char int. So this is what variable function means. So you can say, so a whole overloading set is a function with the same name, right? Forget about context. ADL may reach other functions, but they are functions with the same name. And the variable functions set for a call is a subset of the overloading set that might accept that call. So I changed my hope a little bit. The functions that may exist in the set may accept that call. May accept the same call. Should give schematically the same output. So let's go back to the issues we met. First, still move. The casting one still move has dedicated to accept one argument. The algorithm one accepts 3. They will not be able to be in the same variable function set for any call, right? You can't have a call and gives both one argument and 3 arguments. The next thing is about constructors. I forgot I can't show you the standard. So if you go look at the constructor of unique lock, I can show you CPP reference. This is good. You see, unique lock has 8 constructors, and many of them are not doing the same thing. If you look at 3, 4, 5, and they say the 3 locks the associated mutex byte, blah blah blah. This gives you side effects, right? And the 4 does not lock. Now they have different side effects. They don't have the same output, right? But we have to overload them because they are constructors. And this is how standard solves it. we define a empty class to represent a type. It's called defer log t, try to log t, adapt log t. What's the purpose of these types? They can put those overloads in a different variable function sets. Although they have the same number of arguments, but we assume people don't have like implicit conversion to these label types. That's insane. That doesn't make sense. And we have the standard has a similar technique to solve this, like piecewise. I think I should just show you the pair constructor. You see, here there's a piecewise constructor T. What this does, for the same purpose, they can put, again, they can put this overload into a different overloading set because it has one more argument. And it's same for the allocator arg underscore T for the same thing. Where is my slides? Okay. So, here's how I answer the question. First, try to design your function overload set as one function. Try, but you might not get it. You're not going to be able to disambiguate every case because, like the piecewise constructor T stuff, all other arguments are parameterized, have the same number. You have the same input type. How you disambiguate that's impossible. But we have workaround. We can we can change the number of inputs. If you cannot make it, make the first one, try the third one. Design your variable function set as one function. So that's the first part of this talk. We're done with design. Any questions so far? Okay. Yeah, about half. Now let's jump into the techniques part. The first one is not quite a disambiguation techniques, but just a tool. But it's a very important tool. Why is it important? Because it suddenly solves 50% of our disambiguation problems. Why? As I showed you, my definition of disambiguation is to avoid the unintended exclusion to be reached. And avoid means we can cut this off or we can change it. And this one cuts the possibility off. Your code just don't compile. And the best part is it works with spinning in a very nice way. Well, what spinning is, you probably know, but we're going to talk more about it later. And if you want to remove a function from an overload set, never use static assert. That's for a totally different purpose. And if you know spinning, you probably know static assert give you hard arrow. But as I said, design is more important than techniques. I'm going to talk about static assert later. So this technique, let me give you, let me see whether I can find an example. Okay, there we go. reference wrapper constructor. This one is copy constructor, no dots. The first one, since reference wrapper takes L value reference t, that's what the first one does. And if the t already has a const, this signature becomes const t. That's fine. Wait. What if I have a reference wrapper of constant? Now it can bind to both L value int, an object of int, and a literal of int, right? I can write code like yeah, I prepared on my own computer. I have to say, okay. So what about the color? Okay. English too. Maybe this. Oh, okay. So, if we have a const ref or a reference wrapper of a const reference, then I'm going to be able to capture a R value reference. Why is that a good thing? Because const t ref can extend the lifetime of the object, but const reference wrapper is not a reference. It's inside is a pointer. The pointer does not extend the lifetime. So anyway, the reference wrapper is designed to capture only L value reference, not R value ones, no matter how this T is defined here. So that is what we have, what we do. It's something I'm very proud of about standard. It's different from Boost. Boost does not have this. What this does is it captures the R value reference, R value, and delete it so that your code does not compile. You have no dangling reference just because you used a const type in reference wrapper or something. So, as you can see, it's a case of use that's removing a overload from a overloading set. This is because we consider it as illegal. The equal to delete thing can be, as I said, it solves 50% of the problem. It can be combined with all other techniques we are going to talk in the rest of this talk. So here is the actual techniques we're going to use to solve ambiguation problems. First, the most simple one, you have already seen it. Add one more overload. Here's an example. Do you know what string view, the new string view is? Yeah, right. It's a string-like class, but it has reference semantics. It can be implicitly convertible from both character strings and string. So when you're writing function parameters which might take a string, you don't need to write both. But think about it. If I already have a function, I only have I only have the first function in my old code, and just because I don't want to change the API of my original code, to adapt to new API, I added a string view overload, because someone might pass string view around, right? What happens? Yes, exactly. Your problem, yes, the answer is right. The problem is, if I only have those two overloads, you are not going to be able to pass a character string to that function overload set, because language considers ambiguous, because string takes that, string view also takes that. It's an obvious ambiguous. And they actually really found a case of it. Look at this, right? st2r. Almost all other functions in the standard accept both const reference to string and a character string, but this does not. When we are adding new string view overload to it, we are going to have to duplicate all those overloads twice, one for string view, one for character char. And if you have ever looked at an early version of the string view proposal, when we are still trying to fix adding overload to the whole standard, you're going to see this as unusual. Yeah, the most basic one. The good part is it does not break API. When being compiled with delete, you can delete one overload. Downside is scalability. What I mean by scalability, for each type, you have to, the first problem about scalability is, for each type, you have to add one overload to it. If you have multiple types, you are going to have to add multiple overloads. And look at this. This is pre-C++ 11. So you see, standard also has lots of bugs. In the old definition of toString, we have three overloads: long double, unsigned long long, long long. That it looks like that covers all, because all other arithmetic types convert to them, but ambiguous. Why? Int can implicit to convert to both signed version and unsigned version. Here comes the scalability problem. For all those arithmetic types, you're going to have to add those overloads at every places. And the more severe scalability of problem is that not just two string. Think about it. We have many functions taken from C, right? We have ABS, we have lots of them. And the standard says we are going to overload for all of them. Hopefully ABS does not work for unsigned types. I like it. But if one day we have long, we're going to have it in every places. It looks like we need a concept for this thing and solve it in one place, right? So that is the two parts, but both sides of the scalability problem of this simple solution. Capture one type. We are going to solve the problem later in this talk. And here's the next technique, capture all the others. I don't have enough time. This is like a capture all template. It's unspecialized. I think I hope you already read Hofstadter's old article. Never specialize function template, right? And you know why? Because when doing template and doing overload resolution, only if the base template is being selected, its specialization is going to be considered. Otherwise, its all specialization doesn't count. The normal functional overloading takes a priority than the specializations. But that doesn't mean we cannot use both functional overload and specialized template together, right? When we are doing that, we got an effect. I call it general specific design. You have one thing that captures all the other cases, but specific overload for each others. It also does not break API. But there is a side effects. You might want this, and you might even want to make use of this, but if you don't, you are not intended to use this, you are in trouble. Implicit conversions are turned off on this variable function set. For example, if you have a function which takes a function of write, takes a string, and you have a capture all at case, then your character string to string conversion are automatically gone. You're never going to reach that because the capture all case capture all the others. But we might also want to make use of this side effects to disable all the implicit conversions, and we do have a use of that. Let me show you. Let me see. Anyway, I think I don't have time to find. I know where those examples are, but it's not my computer. I'm not going to show you case by case. Sorry. I'm going to explain it in the network byte ordering proposal. We have byte order conversion functions, and they are supposed to work only on bytes, right? They take only unsigned integers, and what we do is we create overloads for unsigned integers, type by type, and we have a capture all case and delete it to disable all other implicit conversion from any object to unsigned integers. Like if you have an long, it's not going to be implicit convert to unsigned long. And I think, I'm not sure whether CPP reference website is updated. If you look at make unique, we removed all the overloads that you might expect it to give you a re-specialization of the unique putter. Both tactics we discussed before are based on effects. It's in the object you're going to talk, changes overloading, it's in the arguments. But there might be a case they're not in the arguments. They are objects as your class member. How do you deal with that? Here's the way. Create an empty class called identity. The definition of identity is just this. Empty class. It has a title for that. What it does, it represents the uniqueness of the type. There's a one-to-one mapping from your T to the type of identity. And you create an object of that and use that like shadow object to deal with overloading resolution in your implementation. We'll use this. This can solve the problem that you don't have an object. And it has another use case, which is very important, and I'm going to show you very late. Just be aware. One thing you need to be aware of that is, in many cases, if you like a function takes a generic type T as value in your function, the the argument adjustment, like L value to R value conversion, array to pointer conversion, those still comes in, although they might be right, but for consistency, we often, when they don't come, we have to use decay, like Nico showed. When we are taking T-ref, there's no L value to R value conversion for when the function is taking reference. We need to use decay to fix that. But for this one, if you use identity, it's really identity. There's no R value to R value conversion, so you have no the CV qualifier of a type is not stripped out. If you have const T here, you're going to be able to be overloaded on const T, the const part of the T. That might not be the thing you want. So be aware of CV qualification, but don't worry, we have type functions to remove const qualification, like remove CV, right? And we can do decay. This is the definition of type function identity, and we have a proposal to standardize this. But there are other use cases of this function. I don't have time to expand, but if you look at this proposal, you'll find that it's very useful. It has many aspects of its use. Sometimes the problem is not on overloading resolution. The ambiguation is caused by temporary argument deduction. Does this work? Yeah, I think I should make my slides more interactive. Okay, but why? It seems that I'm just forwarding the pushback call by value, and it's T in it takes any type of stu vector and its element type, and if I do v dot pushback here, that obviously work, but this does not. Why? Because it's the element of long. This is int. The reason it works in the reason it works, if we don't do the forwarding, if you tap back to, push back, it looks like the function signature is the same, right? It also takes a T, but that's not quite true. This T is not the template argument. It's not in the deduction context. There's nothing to deduction because this is part of the class type. So this function basically like const int reference. There's no deduction here. But if we go back, look our free function case, this is the template argument. It jumps into deduction. And the template argument deduction says those two T's need to be deduced to the same. And apparently they are not the same. Fix identity shines here again. Identity can disable the template argument deduction. You can put the template argument deduction into non-deduced context. If you want to know why I have some reference at the end of slides, you can point to STL's talk. It can also be used to enforce user to pass a template argument deduction, but to pass it to as a template argument because it's not deduced. And if you look at the definition of stu forward, that's exactly what it does. Okay, so what we learned so far is we have specific, we have solutions for many overloads, that's many specific case, and we might have capture all case, which is general specific in the interface. This one is a little bit different. It's a constrained general interface. When I say constrained, I mean this one is not constrained. It can accept any type, right? Open to the world. But this one is. And by the way, this code is in C++ 14 style. If you are still using C++ 11, you don't have enable if t, just have enable if, and you're going to need a type name in front of that. That looks really ugly, but it's still kind of readable. Let's try to read it. If you go look at standards, when it has a lot of wording like this function should not participate in overload resolution unless blah blah blah. For this case, t is not a POD type. That's if you see this in remarks part in the standard, pretty much it mandates you to use this technique to constrain a class a template which open to the world. But I only have 20 minutes left. I can't do this. What I wanted to do is do a live coding of how to write this finding. But you can look it up on the CPP reference website. If you go search for spanning, it will bring you to a page called spanning and explain what it is and how to write it. But it's okay if you even don't know how to write create a spanning case by yourself, because in a standard library you have type traits, you have meta functions, lots of things that you can just start to use without knowing what the hell this is. And at least the common styles you might want to use. This style, you can put the spanning trigger, enable if, in the return type place, because by default, this class template give is a creates a type of void. And so if your function happens to return void, you can just put it there. And what's funny is, I forgot to say, substitution failure is not an error. If during the substitution process of enable if t, there is an error, but not hard error happens, the overload, the substitution process discard this signature to others. So that is how it's called constraint. It's limited to the criteria you specified here. You only work, this function is only selected if that criteria is met, just like the standard say. Read it as this function should not participate in overload resolution until this is true. And we have lots of type
So, just a question. The enable if thing expands in essence to void if it's valid, right?
Yes.
So you end up having a second parameter.
Yes.
So in principle, you could mistakenly write code that passes in a pointer as a second parameter.
Yes. That is why I always wanted to, the question is, by using this style, you have one more parameter, although it's default, and user might pass one more parameter into it and think it's meaningful, while it's not meaningful. So that is why I always prefer to use a return type form of this. But as you can see, constructor has no return type. It's a place you have to use some style. May not be this, but no style is perfect. We're going to see more. Right. This is style. This is style that only works for C++11, because we say not just the template, argument, function parameter, return type can involve into the spinning. We also say the creation of the template argument type also do. So you can inject it here. But as you can see, you always have to inject some types. It might not be the function parameter type. It might be template parameter types. But it's a little bit better. About last style. The last style may cause this template redefinition problem. But I still prefer that style. Because you see, there's nothing more than the things I want to express, inject here. What this int is, right? It's pointless. But with this, we have no name, and it's just a spinning trigger, and I can read it in English without ignoring anything. And the reason I don't worry about the template redefinition problem is that this problem only comes when you use spinning wrong. I will tell you other better solutions to if you meet this issue. And as I said, spinning is substitution failure is not an error. Substitution only happens on template. If your function is not a template, and if you still want to use spinning, you can still do it. Just make it a template. Right? Okay. That's the problem with it. You go read Eric's article about it. Because special member functions are dedicated to functions. If you write a template, it's not considered as a special member function, and the compiler might still synthesize once for you, and they might ambiguate finally. So, but we have solution to that. So what spinning is, how you use it, right? Spinning is a hammer. It can solves almost all the problems. If any overloading problems cannot be solved, let me say this: if from your point of view you might be able to disambiguate the function call. Like they have different inputs, right? And that cannot be solved with finding. Then there's a problem with the standard, within the standard. Like we did not fail to design to the language very properly. There are some cases, but I don't want to explain. Finding is a harm because it, you can use it to program the language rules. Like Gabriel said, although for a different purpose, the voting like should not participate in overload resolution. Likes to say, the language rules just don't work here. Sounds like that. It's kind of scary because this is a library solution. How a library solution can change the language definition, right? But that's the charming part of C++, right? As I said, finding can be used to solve pretty much any problem. But if you really use it to solve any problem, your code is going to be really, really ugly. Like, for this, in Chandler's talk, he says he has many ugly codes, and he might have to want to customize for each container type by type. And in my mind, it's not the code he writes, but it's a code I wrote. In my mind, when you say ugly and it solves the problem case by case, and you use finding, you're probably going to run into this, right? We just make all our function templates, and we put finding triggers on it, and we use type functions to evaluate, see whether it's the same thing, see if it's not the same thing, because we are not using any existing overloading resolution rules here. We just create ambiguous templates and program it. No, right? Don't do that. All you need, as I said, is a identity dispatch. That's it. As we've shown, it can be used in implementation. If you don't have the object, create an identity of that, and use that identity in overload resolution. You say, in this is a general case. It captures all the others. Why capture all the others? Because this is overloading. If the type the uniqueness of the type is zero least V, then this is overload is triggered, reached. This is vector, and if all others, this one jumps in. So this technique is very useful. You can save lots of your things from using finding. So try to use overloading resolution to solve overloading problems. That's like saying nothing, right? But that's what we should do. Use finding as the last result. Okay, patterns seen so far. They have specific only interface, have general specific interface, and we know how to constrain them. And I also showed you an example which overloading resolution itself is better than template method programming. And if your overload set is complex enough, each base template may choose different type of interface. But fortunately, if the base template is not ambiguated, when I say ambiguous of templates, I mean after the function template's partial overloading finishes, there's one base template is selected. We'll call it ambiguous in base templates. So the fortunate part, if your function template, your all your base templates are not ambiguous, your solution, your overloading resolution or spinning does not jump across those base templates. They are dedicated to them. So it's a problem to function template specializations, but not for us. We are using these rules. And because the overloading resolution does not jump across function templates, you can treat function template as your subdomain of your design. So look at the patterns we've seen so far. Specific only, general specific, constraint general specific interface. There's one more. Multiple constraint general interface. How to solve that? You can imagine you have one or more base templates and they are ambiguous. So your overloaded resolution do jumps across those. How to solve those? How to solve this problem? Here is a refer. To solve this, we need to look closer to the spinning or the thing we are going to do, template metaprogramming. For template metaprogramming is not much different from your normal programming, and it do have some benefits, right? It has no side effects. Very functional. We have for template metaprogramming, we have type functions, and some of them are control flow, some of them are predicates. When I say predicate, I mean something like stu is underscore in the standard, like is port, is const, is pointer. They take type as their template parameter and return type, and the type is a integral constant. The integral constant is Boolean. That is why they are called predicates. And we have type modification and transformations, which generally takes one time, transform into another, like remove CV. It removes the const volatile qualifier from a type. And if you are an MPL user, you probably know there are higher order function type, higher order type functions, but they don't have something in standard. We don't have MPL data structure either. And before jumping into it, yeah, so let's pick up the topic I raised that earlier. Why you should not use static assert here? I will try to write this code like this. And what happens here? I created this is the obvious general specific interface, right? This constraint general specific. This one, not quite. Yeah, this is general specific interface, and you will know later why. We take any type, make an unsigned type of it, and we have our own big integer types. We also want to convert it to unsigned, but it's not unsigned big integer. We call it bits. So we customize this specific case. What's wrong with it? If you compile this code under libc++ and probably GCC, it actually works fine. But if you replace do make unsigned with boost makes unsigned, it gives you an error. Why? Oh, I forgot I can't show you the standard. Go find in the standard go look for make unsigned. see the description part, there is a tiny little wording at the end of the description. It says requires. T is a integral type for emu, but not bool. Requires. We don't usually see this in type functions. We know what it means in the runtime functions. Requires a precondition, right? If you violate this, it's an undefined behavior. What happens if we put requires on type functions? Well, obvious, that's a compiler on undefined behavior. So type functions may have precondition. Be aware of that. And static assert is an approach, not mandated approach, to denote a precondition violation at runtime. So that is why you should not use it for disambiguation purpose, because it does not disambiguate. Disambiguate means we know your input is right, and we are able to add it to another. This one is a precondition violation. It's for a different design purpose, and you probably know it causes a hard error, and hardware error is not captured by spanning. And when it comes to a type function, of course we can have we can add static assert to make unsigned, because it's designed to make those behavior outside the picture. But if a function says it has no requirements, it's white contract, and you use static assert on inside, that's very evil. That's wrong, because you are violating a contract you established by yourself, and we call this finding unfriendly, or just not finding friendly. Finding not unfriendly is wrong. We will fix all those cases, definitely.
Sorry, so the point was that difference between standard make unsigned and boost make unsigned is that the boost is using static assert for bool?
Static assert for something that is a bool or not an integer. There's no difference between the design of boost make unsigned and store unsigned. The difference only appears in implementation, and I think the library vendors should just add those static asserts. There's nothing wrong with the standard or the. It's as I said, it's a contract. It established a contract. It's a part of design. And the good thing part about using template programming here is that we have scalability. You can establish concepts and use them everywhere. You don't need to change overloads one after each, everywhere. It sounds like one ring to rule them all. It's nice. And be great. I don't have time. Let's skip this. You can find this material on Boost website. If you go search for Boost enable if, there's a chapter explaining this problem. But the only thing it misses, it only shows there is a problem, but it does not explain why. I have a proof to say this problem always happens. There's no case it does not happen. So when meeting those problems, as I showed to you before, you have to have you have to have duplicate predicates to because the problem is the function template. The template is ambiguous. They are in the same type space, and when you are using spanning on it, you have to make all those constraints disjoint, which means for here you have each integer. The rest one is not going to capture all the other cases. Instead, it's ambiguous. You need to make those constraints disjoint in this way, like not is the integer. And if there are multiple characters here, you have to have all those characters repeated in your picture. And if you don't want to see that, if you go look at Chandler's talk, there is some code like is, and later you'll find enable if is not, and something like that. No, don't do that. Use this. We solve it with an overloading. So turn it into an overloading problem, not a spanning problem. As I said, those type functions create a type which represents a Boolean, and those type identity to true and false. We call it stu true type and stu false type. So we can create an object in it, and you create more implementation overloads, and this object will automatically select based on this criteria. There is no spanning involved here. And if you have multiple criteria mixed together, some of them make sense, some of them does not, you can just put those criteria, create objects for each one of them, and have implementation overloads, which takes all those things. And if you find something that really doesn't make sense, I don't care. You can put ... here. The ... is not template variable variadic template. It's just C ... is used to ignore the arguments, and it takes very low precedence in respect to all other overloads. So if all other overloads is not selected, like for this case, this one with the explicit type is selected before the one you put ... So the syntax actually finally looks very nice. Last part is very short. Although this technique is very advanced, tag dispatching. I'm not going to explain how you implement a tag dispatching. If you go look at, if you want to know how to do that, you can look up. There are many books and articles related to iterator category. They'll tell you how to do that. And last year, Joe has a talk about an automatic framework to create tag dispatching. That's wonderful. But I'm going to talk about some essences of tag dispatching. Why this solution work? If you look at identity, it represents a property called uniqueness, right? Each type mapped to an identity is identityness. If you have type predicates, we map all those types into two categories, right? If we have a type function that with like 3 types possible return types, that's going to be interesting. And that is the essence of tag dispatching. We create a isomorphic structure of the original type. If we create some structure here, and it can represent some property in the original type. Like for this case, we say T2 is implicitly convertible to V1. V2 is implicitly convertible to V1, and we create all those objects of the return type of Ft is split into 2 categories. and the object do implicit convertible to the larger possible value set. And because they are isomorphic, we can say the original type also has this property. In that case, we say TA refines B in terms of our type function. This is the essence of tag dispatching, which is refinement. And hopefully we can get concept light in a near future, and concept light support refinement-based overloading resolution, so you can forget what tag dispatching is, but since we know what refinement is, you can use it. Use the same idea, but implement it with concepts. Yeah, I'm done. So, conclusion. Design overloaded function set as one function. Design my patterns. I showed you patterns. Solve them by patterns. And try to use more overload resolution to solve overload resolution problem by itself. And finally, can pretty much solve anything. Use it at the last. And I have some reference if you don't know the details or some actual materials in this talk. Questions?